In the last video, I started to talk about the formula for curvature. And just to remind everyone of where we are, you imagine that you have some kind of curve in, let's say, two-dimensional space, just for the sake of being simple. And let's say this curve is parameterized by a function s of t. So every number t corresponds to some point on the curve. For the curvature, you start thinking about unit tangent vectors. At every given point, what does the unit tangent vector look like? And the curvature itself, which is denoted by this sort of Greek letter kappa, is going to be the rate of change of those unit vectors, kind of how quickly they're turning in direction, not with respect to the parameter t, but with respect to arc length, ds. And so what I mean by arc length here is just a tiny step. You could think the size of a tiny step along the curve would be ds. And you're wondering, as you take a tiny step like that, does the unit tangent vector turn a lot or does it turn a little bit? And the little schematic that I said you might have in mind is just a completely separate space where for each one of these unit tangent vectors, you go ahead and put them in that space, saying, okay, so this one would look something like this. This one is pointed down and to the right, so it would look something like this. This one is pointed very much down. And you're wondering, basically, as you take tiny little steps of size ds, what is this change to the unit tangent vector? And that change, it's going to be some kind of vector. And because the curvature is really just a value, a number that we want, all we care about is the size of that vector. The size of the change to the tangent vector as you take a tiny step in ds. Now this is pretty abstract, right? I've got these two completely separate things that are not the original function that you have to think about. You have to think about this unit tangent vector function. And then you also have to think about this notion of arc length. And the reason, by the way, that I'm using an s here as well as here for the parameterization of the curve is because they're actually quite related. And I'll get to that a little bit below. And to make it clear what this means, I'm going to go ahead and go through an example here where, let's say, our parameterization with respect to t is a cosine-sine pair. So we've got cosine of t as the x component, and then sine of t as the y component. Sine of t. And just to make it so that it's not completely boring, let's multiply both of these components by a constant r. And what this means, you might recognize this cosine-sine pair. What this means is that in the xy plane, you're actually drawing a circle with radius r. So this would be some kind of circle with a radius r. And while I go through this example, I also want to make a note of what things would look like a little bit more abstractly. If we just had, s of t equals not specific functions that I lay down, but just any general function for the x component and for the y component. And the reason I want to do this is because the concrete version is going to be helpful and simple and something we can deal with, but almost so simple as to not be indicative of just how complicated the normal circumstance is. But the more general circumstance is so complicated, I think it'll actually confuse things a little bit too much. So it'll be good to kind of go through both of them in parallel. And the first step is to figure out what is this unit tangent vector. What is that function that at every given point gives you a unit tangent vector to the curve? And the first thing for that is to realize that we already have a notion of what should give the tangent vector. The derivative of our vector valued function as a function of t, the direction in which it points is in the tangent direction. So if I go over here and if I compute this derivative and I say s prime of t, which involves just taking the derivative of both components, so the derivative of cosine is negative sine of t multiplied by r, and the derivative of sine is cosine of t multiplied by r. And more abstractly, this is just going to be anytime you have two different component functions, you just take the derivative of each one. And hopefully you've seen this. If not, maybe take a look at the videos on taking the derivative of a precision vector valued function. And this we can interpret as that tangent vector, but it might not be a unit vector, right? We want a unit tangent vector, and this only promises us the direction. So what we do to normalize it and get a unit tangent vector function, maybe a different color, and get a unit vector tangent function, which I'll call capital T of lowercase t. That's kind of confusing, right? Capital T is for tangent vector, lowercase t is the parameter. So I'll try to keep that straight. It's sort of standard notation, but there is the potential to confuse with this. What that's going to be is your vector value derivative, but normalized. So we have to divide by whatever its magnitude is as a function of t. And in this case, in our specific example, that magnitude, if we take the magnitude of negative sine of t r multiplied by r, and then cosine of t multiplied by r. So we're taking the magnitude of this whole vector. What we get, making myself even more room here, is the square root of sine squared. Negative sine squared is just going to be sine squared. So sine squared of t multiplied by r squared. And then over here, cosine squared times r squared. Cosine squared of t times r squared. We can bring that r squared outside of the radical to sort of factor it out, turning it into an r. And on the inside, we have sine squared plus cosine squared. I'm being too lazy to write down the t's right now because no matter what the t is, that whole value just equals 1. So this entire thing is just going to equal r. And what that means is that our unit tangent vector up here is going to be the original function, but divided by r. It happens to be a constant. Usually it's not, but it happens to be a constant in this case. So what that looks like, given that our original function is negative sine of t times r and cosine of t times r, we're dividing out by an r. The ultimate function that we get is just negative sine of t and then cosine of t. And for fear of running a little bit long, I think I'll call it into this video and continue on with the same argument in the next video.